Okay, congratulations. You guys have made it to the first exam. I guess maybe condolences. Regardless, to help you guys prepare for it, you have an additional assignment this week that's just the exam one review. So hopefully you've started it. But what I want to do in this video is highlight a few questions from this review that I wanted to kind of talk about with you guys. In order to keep the video short, I can't do every single problem, but a lot of the problems you'll see are very similar to the homework, and so you can use the homework to kind of reference it. Regardless, though, if you have any questions as you go through the review, please reach out. Please email me. Please join my office hours via Zoom. Whatever you'd need to get the help on those problems that are confusing for you. Okay. So once again, I just want to highlight a few different questions, and so if you want to follow along with your homework, that would be awesome. So the first one I want to look at is number 10. Okay. Everything before this is all just limits, and this is also limits. Okay, so there's lots of different examples of lots of different problems just talking about how do I evaluate limits from a graph, from functions. Here we have a piecewise function, okay, because you have two different rules depending on what your x value is. But this one's a very interesting one because the rule only changes at a specific x value. And everywhere else, it acts like this function right here. Okay, and this one doesn't ask us for limits. It just asks the question, is the function continuous at x equals 8? That's all it asks. Okay. So what might we want to do here? Okay. Well, in order for this to be continuous, what do we know? We know that means the limit as x approaches 8 of the function, well, sorry, in this case the function is capital G of x, of the function has to equal the function value at that point. Right? That's our definition of continuous. Well, what's my function value? What is G of 8? Well, according to my piecewise function, and in my case, of course, your numbers are going to be different. I just want to clarify that. This is the problem it gave me, but it changes the problem numbers for everybody. According to my problem, when I actually plug in 8 for x equals 8, I get 16. So the whole point of this problem is to check to see whether the limit as x approaches 8 of my function is equal to 16. Well, for my limit, if I'm concerned about my limit, which part of the piecewise function am I looking at? I'm looking at this piece. Because if I'm taking the limit, I'm looking at x values close to 8. So values that are not equal to 8, which means I'm looking at the other part of my piecewise function. So what's my, kind of boils down to this question. What is my limit as x approaches 8 of x squared minus 64 over x minus 8? I, of course, have a discontinuity here, but you'll notice I can factor the numerator. Okay, so I'll factor the numerator and I get x minus 8 times x plus 8 all over x minus 8. The x minus 8 factors cancel out, and I'm left with the limit as x approaches 8 of just x plus 8. And since that's continuous at 8, I can go ahead and just plug in 8, and I get 16. Does that match? It does. It matches. So, in our case, at least for my problem, since the limit matched what the function value was, the function is continuous. Okay. Feel free to pause and work through your problem, and then I'll start on the next one. Okay, next I want to look at problem number 11. So the very next problem. Okay, so number 11, now we get into average rate of change. Okay, the reason why I want to talk about this one is in order to be able to answer this problem, you have to be able to take a close look at the graph. Okay, but this will also be a good reminder of how average rate of change works. So To just put it simply, we're going to use the graph to estimate the average rate of change from 1994 to 2000, 2000 to 2006, and then 1994 to 2006. Okay. Well, that means, right? So let's just think about my average rate of change formula. My average rate of change formula is change in Y over change in X. Well, in our case, what is X? Okay, X in our case is years. How many years has it been? And then change in Y, in our case, is the percents. Okay, right? Because we're measuring the percentage of new employees. Okay, so it gives me the X values. It gives me the years. How do I figure out the percentage? I use the graph. Okay, so let's look closely. 1994. What's my percentage? Here's 1994 is where it starts, so my percentage is just 0. Okay, so I have a coordinate point now for that very first point. Okay, I'm also going to need to know my coordinate point for 2000. So here's 2000. I'll come up here, follow that line over, and I'm left at about there. So I'm going to go and call that 18%. Okay, that gives me my next coordinate point, 2000 and 18%. Last but not least, I also need to know 2006. I'll follow that one, and I get this point right here. Follow that line over, and I think you get about 22. So my last coordinate point is, 2006 and 22%. Hey, that's kind of the hardest part of this problem, is just making sure we get those coordinate points. Because now once we have those coordinate points, let's go ahead and look at 1994 to 2000. Okay, I take my change in Y. My change in Y represents the change in the Y values. So 18% minus 0%. And then change in X represents the change in years. 2000 minus 1994. I get 18% over 6, which I simplify, and it just gives me 3% per year. Very nice. Okay, and I'll do the same thing for the other ones. For 2000 to 2006, I get 22 minus 18 over 2006 minus 2000, which gives me 4 over 6, 4% over 6, which, this one's interesting because you do have to round. So I get 0.6, what does it say over here? Round to 2 decimal places. So since this is 0.6 repeating, I'm going to round it up to 0.67% per year. Very nice. Okay, and then I can do something very similar for 1994 to 2006. So that's average rate of change. And there's a few more problems where you have to look at a graph in order to get those points, but a lot of times the points are actually given to you. This one they're not, so I wanted to kind of walk through that with you. Okay, go ahead and pause your video and work on that problem, and then we'll meet back together for the next one. Okay, the next problem I wanted to go through is number 14. And the reason why is I'm not sure I talked about this idea of differentiable. I'm not sure I talked about this idea at all in class. So what does it mean for a function to be differentiable? That just means if it's differentiable, it means you can take the derivative at a point. Okay? So there's a couple criteria that we're looking at in order for a function to be differentiable. Well, in order to be able to take the derivative, first off, taking the derivative requires, using the difference quotient requires me to be able to find the function value at the point. So if my function value doesn't exist or is undefined, I can't actually find the derivative. So first rule of thumb, the function must be continuous at the point. So first off, that has to be true. The function has to be continuous at the point. So take a look at this graph, and I can go ahead and cross out points where the function's not continuous. At x1, we have an asymptote. We have a vertical asymptote. Here, instead of crossing it all the way out, I'll just do this. At x1, we have a vertical asymptote. So my function's not continuous there, and therefore my function, I can't find the derivative at that point. At x2, I have a hole. And even though that function still seems pretty smooth, because I don't have a function value at that point, I can't find the derivative. So x2 is also not differentiable. Where else do I have a discontinuity? At x4. At x4, I have another hole, which means I can't take the derivative at x4. It's not differentiable. Okay, well, there is a second piece of criteria to whether a function's differentiable or not. Okay? And that is the function must be smooth at the point. What do I mean by that? Well, take a look at x3. Take a look at x3. What do you notice about the function at x3? It has this weird angle. It has an angle happening. If I asked you to find the tangent line at that point, could you do it? Not if it's an angle like that, right? It's impossible to draw a tangent line at a point where there's an angle. Because I can't draw a tangent line, I can't find the slope of the tangent line, which means I can't find the derivative. So my derivative would also not exist at x3. So let's look at my last 2 points, x0 and x5. Is my function continuous at those points? Yes, you see the closed dot. Is my function smooth at that point? Yes. If I wanted to, I could draw a tangent line. I could draw tangent lines at both of those points. Therefore, my function is differentiable at both of those points. X5. Very nice. Okay, pause the video, go ahead and work on it yourself, and then we'll go ahead and press play when you're ready to move on to the next problem. Okay, so next we get into actually calculating derivatives. Okay, so before this, there's a few more problems like 16, 17, 18, 19. They're all just calculating kind of more basic derivatives, just using your power rule. I think 16 technically you could use chain rule to help you out, but you don't need to as long as you know like square root properties and things like that. But here we have number 20. I wanted to talk about this one because we really haven't seen this notation very much. Okay, so I just want to be clear about what this is asking for. This is asking dy over dx. We have seen that before. That's just the derivative. So what this question is asking for is, what's the derivative of this function? And then we're going to evaluate it at x equals 1. So what's the derivative of this function at x equals 1? Okay, that's what we're going to do. Now, this one it doesn't look very complicated, but it's easy to get mixed up with this one. The key to being able to take the derivative of this problem is just being able to rewrite it effectively. Okay? If I have a power in the denominator, I can rewrite it using a negative exponent. But we have to be careful because I don't want to rewrite it like this. Oopsies. Ooh, no. I don't want to rewrite it like this. Okay. Why not? Because the 7 isn't affected by the exponent. The 7 needs to stay down in the denominator. I can't also bring the 7 up. I only bring the x up. So instead, a really effective way of writing this is keeping the 1/7 as a fraction and then writing x to the -2 as its own kind of thing. Okay. Why is that helpful? Because now I can recognize that 1/7 is just a constant, and then I can focus on what's the derivative of x to the -2. Okay. And once we can write it like that, then it's just, okay, yeah, now I can just use power rule, and my derivative, let's see, let me write it over here, and my derivative, dy over dx, is, let's see, 1/7. I'm going to bring down the -2 and then subtract one more for the exponent. Remember, since it's negative, it becomes more negative because I'm subtracting. I can go and simplify this by multiplying the 1/7 and the -2, so I get -2/7 x to the -3. Okay, and now, so there's my derivative. And now, once again, all this means is just that I'm evaluating it at x equals 1. Okay, so what does that mean? It just means I'm going to plug in 1 for x. Well, what is 1 to the -3rd? Because my base is 1, 1 to any power is just 1. So I get -2/7 times 1, which is just -2/7. So my answer is -2/7. It does say simplify your answer, but can I simplify that fraction? I can't simplify that fraction anymore. So my answer is just -2/7. Very nice. Okay, go ahead and pause. You can work on that one, and then we'll move on to, let's see, how many more do I have? Just one more. Okay. Okay, so the last problem I want to go through, I think this is either number 28 or number 30. I'm gonna go ahead and write number 28. Okay. This is the last question I want to go through, mostly because this is going to be great practice with the chain rule, but also it talks about tangent lines again. So this will be a good reminder of how tangent lines work. Okay. So we want to find the equation for the tangent line to the graph of, and it gives me an equation, y equals x cubed minus 9x all raised to the 8th power at the specific point 3, 0. Okay. Well, if we remember, there's a couple of things to keep in mind when we see that word tangent line. First, the slope of the tangent line is the derivative of the function. Where? At, in our case, 3, 0, right? At the point that we specify. So in order for me to be able to write this equation, I need the slope, which means I need the derivative. Okay? So I need to find the derivative of this function. Okay, so y prime. Well, in order to get y prime, I've got a function inside of a function, which means I need to use the chain rule. So I'm going to go ahead and declare my inside function as u. Okay, I'm going to call u equal to x cubed minus 9x, and then that means that y is just equal to u to the 8th. Okay? So, a chain rule, if you remember, if I want to know the derivative of y in terms of x, then I can do the derivative of y in terms of u times the derivative of u in terms of x. Okay, so derivative of y in terms of u, I get 8u to the 7th. And then the derivative of u in terms of x, that's the derivative of this function, I get 3x squared minus 9. Everybody okay with both of those derivatives? If you're still confused about these derivatives, please let me know, because that means we're still struggling with the power rule. So let me know if you're still having issues with these derivatives. Okay. Of course, I want this all back in terms of x, so I can go ahead and rewrite this as 8u is equal to x cubed minus 9x. So all of that is raised to the 7th power times 3x squared minus 9. Okay, so there's my derivative. I've successfully got my derivative. And then let's come back to what we said before. The slope of the tangent line is the derivative of the function at my specific point. Okay, so at 3, 0. That means over in my function, I need to go ahead and plug in 3 for x. Okay, because 3 is my, 3 is my x value. Okay, so I'm going to plug in 3. Let's see what I get. I get 8 times 3 cubed minus 9 times 3, all raised to the 7th, times 3 squared minus 9. Well, it turns out 3 cubed minus 9 times 3 is 27 minus 27. And over here, I'm going to have 27 minus 9. Regardless, though, 27 minus 27 is 0. That's equal to 0, which means I have 8 times 0 raised to the 7th times, what is that, 18? But because I'm multiplying, 0 to the 7th is 0, because I'm multiplying by 0, this all ends up just being 0. So, my derivative of the function at 3 ends up being 0. So, dy over dx, evaluated at x equals 0, is 0. So, let's go ahead and start writing my slope-intercept, or let's go ahead and start writing my equation. So, if you remember, I can use point-slope form to write this. So I can do y minus the y value of my point, so in our case 0. Okay. So this is my y value, equals the slope that's this, right? Which in our case is just 0. Okay, my slope was 0, and then times x minus my x value. Right, so that's how I can write my equation. I can use point-slope form. Y minus y1 equals m times x minus x1. Okay. Well, I can simplify this. Y minus 0 is just y. 0 times x minus 3 is just 0. And that's my equation. My tangent line equation is just y equals 0. Very nice. Okay. So yeah, so once again, I wanted to keep this short, so we only went through these 5 problems. If you have questions on any of the other ones, please reach out to me, send me an email, or join my office hours via Zoom, and we can walk through some of these. Just so you're aware, this review has 32 questions on it. The exam will have 25, so a little bit less. It should take you about 2 hours to take. Best of luck, and we'll see you next week for more videos.